So in experiment 2, we're going to look at the pKa, but we're not really looking at the pKa so much as thinking about the different ways in which we can measure it. Physical chemistry is all about measuring things, and we can measure most things in many different ways. And designing an experiment so that we can get the most accurate result or the quickest result or the cheapest result is often what people are after. It's all very well being able to measure the concentration of something with an instrument which will cost £10 billion if you want to be able to do that every day of the week in every lab you own. And so we've got to pick appropriate methods of being able to measure something. It's not always the most accurate, but sometimes it's the most convenient, or it can give a good enough answer. And this experiment's about comparing two different methods for determining the pKa. So what is the pKa? Well, it's an equilibrium constant. It's the acid dissociation equilibrium constant. So if we take an acid, the acid can exist in two forms, the undissociated HA form and the dissociated H plus and A minus form. And the Ka is a measure of that equilibrium constant, and the pKa is just a more practical way of reporting it, because often these values are very, very small. The order of 10 to the minus 7, 10 to the minus 8 is not out of the ordinary, and so they're not always the most convenient to report. So we use this value of pKa instead. Now, what are the methods we're going to be using today? Well, we have a potentiometric method. The potentiometric method is using a pH titration. You've maybe done this in school, but you'll have certainly seen pictures like this. So this is a pH curve, how the pH changes as the volume of base added is increased. And what we have is we can take our turning points of this, and our end point of our titration is halfway between these turning points. It's not necessarily 7, it's halfway between these two turning points. Now, using the Henderson-Hasselbalch relationship, the pKa occurs at half of this volume. And so we can work out our value from our pKa just from looking at our plot that we've generated. The second method we're going to use in this experiment is conductometric methods. We're making use of the fact that the undissociated acid doesn't conduct electricity, but the dissociated acid is made up of positive and negative ions, which can. And so the more it dissociates, the more conductive the solution becomes. Now, if we think about a weak acid, it's an equilibrium. As I dilute it, I'm making more ions. But I've diluted it. So we need to use something called the molar conductivity. This corrects for the fact that there's fewer ions in solution. Now, if I look at the molar conductivity, I'm able to work out the proportion of ions which are dissociated, and from that I can determine the pKa. Now, interestingly, you're going to use a different method to determine pKa next semester. This is a colametric method where you're going to look at how the absorption spectra changes between the dissociated indicator and the undissociated indicator, and from that you can work out the pKa as well. So I hope this experiment gives you an idea of the fact that physical chemistry is often all about finding the most suitable method for what you want to do, not necessarily the fanciest, although I always like fancy, and it's always better with lasers.